Well, this presentation also discusses handling of data packets, but there are quite a few measures one needs to take, uh, or measures taken in the system based on the quality of radio link. The radio link quality in real life keeps varying, and especially with um, mobile environment. If there is mobility active, then the radio link can vary too much. Uh, so this presentation is more focused on non-LOS communication, and especially with mobility keeping in mind. Okay. But there are a few things which can also be applied to other types of wireless communication. Quite a few different but important things have been included in this presentation. So uh, everything may not match well with the title. Like the first couple of slides discusses latency, an important parameter. I sometimes mentioned it. So it is like how long it takes for the data to be transferred from the transmitter to the receiver. It depends on few things, or it is a composition of three different things. And look at the bottom line. The total latency is the summation of propagation time, and then transmit time, and then the queue, or you can say propagation delay, transmit delay, and queuing delay. By propagation, I mean that the signal takes some time to get to the receiver. Of course, there is a velocity of the signal. The electromagnetic wave would take a while, and we already know that the velocity depends on the material properties of the medium. So only varying the medium properties, you can change the velocity. Or you all should understand that it is something close to c. Uh, the propagation time is then the division of distance by this velocity. But this may not be the only factor in calculating the overall delay. Rather, or the total latency. Rather, it also takes a while for the whole amount of data. Maybe you are downloading a PDF file or a video file, uh, which maybe say a few hundreds of megabyte big, and you wanna transfer it to some other part of the world. Then the data uh, link capacity tells you how much of the uh, content you can send per second. So this is what we call bandwidth. Sometimes bandwidth is taken as the capacity. You see, I have written that it is the available capacity of the link. So you all have the experience that to download a big file, you need to count on the data rate, and if it moves from 3G to 4G, you enjoy a better data rate, it takes shorter for you to download the file. So this is how we can calculate the how much it takes for the well. So if I take you can also consider uh, supplying water through pipe from the tank. If you want to transfer the whole water of a tank, the tank has plenty of water, but the water pipe will be narrow. So the if you have a fat pipe, of course you can clear the water tank quicker. So this is the thickness of the pipe whether it is thin or thick, tells you the capacity, like here. How much you can transfer per second, how much water can flow per second. And that is like the bandwidth here, the denominator in this second expression, transfer equal to size by bandwidth. And size may be the whole content of the water tank. So that tells you how long it takes for the whole water to transfer to the other place. Now you see that when you first starting the transferring the water, the first drop that comes to the pipe from the tank takes a while to get to the other end. That is like your propagation time, the first expression. So you must take that into account, and then the how long it takes for the whole water. So this is your transmit time. And finally, there can be some queuing delays, right? Like you know that some for various reasons you may have to store the packets before they can be forwarded. Like there can be some queuing delays at the routers. They don't have the links free right now, so they are storing for a while and then they transfer. So for different purposes, you may have to uh, wait for the link, for the available link to be clear, to be available for you to be able to forward. So this is like queuing delays. So if you also add that you can find out how long it would take for the whole content to be transferred to the other place. That is the total latency. Is it clear? If it is not, please let me know. Then a relevant term is delay into bandwidth product. This is an important factor because it tells you, I mean, for different reasons, it may be important for you to calculate in the system, like how much data you have currently in the link, or at a particular moment, how much you have in the link. So bandwidth is again how much data you are sending per second. Although we are using the term bandwidth, it's not something kilohertz here. Rather, in digital communication, a lot of times people use these terms interchangeably. So how much data you're sending per second? Like the data rate we mean here by bandwidth. So this is the amount of data you are putting into the link per second. And in the link, the data persists for some time. That is the propagation delay. So here the first time delay is nothing but the propagation delay. You see, I have written here what delay is the propagation delay. And if you multiply that with how much you're putting per second, then of course you understand that this is the total content of data you have in the pipe, in the link, like water pipe, how long it takes to get to the other end. If you multiply by how much you're putting per second into the pipe, then you get how much water you have in total in the pipe. So this is like the delay and bandwidth product. And the sender, I mean, the first drop of water will arrive at the other end before this much water has already been put at the sending end, right? You fill up the whole pipe and then you start getting the first drop at the other end. So you see that I've written here the sender must transmit this amount of data before the first bit arrives at the receiver. And a quick example, just for clarification, that the latency is 50 millisecond. Oh, maybe I should have written down here the propagation delay. I'll correct it. It's the propagation delay. Otherwise, it might confuse with the latency that we used in the previous slide. And but these terms are used interchangeably. A lot of times you'd find latency to be used like we have here. And this couple of slides we are covering from the same book that we used for TCP/IP, the book of Peterson. Uh, However, the rest of this presentation today, I mean, today's presentation is going to be very important. But the rest part, we will not be able to always refer to for the refer to some book, because we'll be like it will be sort of an accumulation of different or disjoint important topics. Okay. But a good part is covered from my book on LT. Okay. Any questions so far? Okay. Well, now we're gonna. I need to know whether or not the digital modulation has been covered in previous courses, like the QPSK, 8PSK, COM, 16, COM. Was this kind of things covered before in any course?
Sir.
Was it? Sorry, it wasn't clear. Was it covered or it wasn't? Oh, I mean, are you all have fallen asleep so quickly?
No, sir.
Okay, so could you get my point? Okay, maybe I share the screen and then ask you again. Is the screen visible? It is, right?
Yes, sir.
Okay. Uh, just, I mean, I have a few slides ready. If you say no, it hasn't been covered, then I'll go through them. If you say it has been covered, then I can skip them. The digital communication, say ASK, FSK, PSK, uh, and QAM. Were this kind of things covered in any course before or they weren't? Are you familiar with this stuff?
No, no, sir.
Okay. So
No,
are,
sir. These
are
things
you
are not covered.
okay? Are you completely in the dark or you have some idea? Are you familiar with this term ASK, FSK, PSK? These terms, at least, guys. I cannot hear from you.
Sir, the topics sound familiar, but they weren't covered in details.
Okay, okay, okay. Then I'll go through them, but quickly. Uh, sorry, I was disconnected for a while. Hey, so in the case of analog modulation, you have some analog information signal that you put on a carrier. The original carrier is a sinusoid which varies according to the information signal. In the case of digital communication, you have the original information first converted into bits. Okay, I mean the in the beginning it might be in analog, or in the beginning it might be in digital too. But whether in the beginning the information is analog or digital, it must be first converted into bits. Then you call it digital communication. And then these bits would be modulated. I mean, some carrier signal would be modulated by this information, these bits, and then you can go for transmission. However, before you transmit, I mean, there can be some other, I mean, up conversion of the frequency, and also it can smoothen your, I mean, the, what do you say, the wave shape. Okay, because the sudden changes you cannot transmit. In the case of final transmission, there there cannot be any abrupt changes that will contain very high frequencies. So you'll have some smooth shapes. You can say that the final transmitted signal always looks analog. Okay, so although you may have digital form before, after you have the digital modulation, but there'll be some process to have some smooth wave shape before you finally transmit through the antennas. Now, how you the way you convert to the digital modulation is similar to what you covered before. In the case of analog, you could either vary the amplitude or the frequency or the phase, AM, FM, and PM. Similarly, you can have amplitude shift keying, frequency shift keying, and phase shift keying. But there's an additional type, which is a combination of ASK and PSK, and then it is called quadrature amplitude modulation, or QAM. And you can also combine a number of bits. First, I'm showing ASK. It is also called OOK, on-off keying. So for 1, you give some level of amplitude. For 0, to represent 0, some other level of amplitude. So with these 2 levels of amplitude, you can represent 1s and 0s. Okay, so just 2 levels of amplitude will be there, and you have then the modulation done. In the case of frequency, you can have 2 different frequencies to represent 1s and 0s. Then it is frequency shift keying or SK. In the case of ESK, your start phase will be different for different frequencies and for different information. 1 or 0, your start phase can be 0 degree or 180 degree. But in this case, you can also include multiple mates. Like with digital communication, it is possible that you combine multiple bits. At the same time, you transmit more than 1 bits. Like here, instead of just 1 and 0, as you did before, every time you send 2 bits. And with 2 bits, we know that there can be 4 different combinations. So for each of them, you assign a particular start phase. So instead of having just 0 and 180, you have 4 different start phases: 0, 90, 120, and 270. So you can identify whether, which combination of the 2 bits are is currently transmitted. So this is how you are transmitting multiple bits together. And then when you have multiple bits in the same atom, it is called symbol or baud. The terms I'm writing down in the chat box: baud or symbol. So that, instead of bit rate, you can call symbol rate or baud rate. Okay, you can say symbol per second, SPS, symbol per second. And you can have even 3 bits. Okay, no problem. So it is then called 8 PSK. If you have 2 bits with phase combination, then it is 4 PSK. It is 8 PSK. This one is also called QPSK, quadrature phase shift. Okay, so 8 different start phase values, equally spaced. Then you can also have a combination between a PSK and ASK. Then it's called quadrature amplitude modulation. Like, you can give different phase values and at the same time different amplitude values. That's how you get different different combinations. You represent different combinations. All you need to do is to represent different combinations. Like here, say 16 QAM. So you have 16 different combinations to represent, meaning that the number of original bits will be 4, because 2 to the power 4 is 8. For 3 bits, you have 2 cube or 8 different combinations. So you need 8 different positions. But if you can have 16 different positions, then of course you can express 16 different combinations while transmitting 4 bits. 4 bits can have 16 combinations, right? So you see that different amplitude levels and different angles are taken. And the positions, when you take this way, is called a constellation diagram. So the bottom three figures are three possible constellation diagrams for 16 QAM. I'm again writing down this term, constellation diagram. So you see that in a single atom, you're sending now 4 bits, and that will be more efficient then. Your actual data will be much higher, right? So the number of bits in a symbol dictates the actual bit rate. If it is higher, you have better bit rate, it's more efficient. Then what is the issue? You just keep increasing it. Well, it's a problem if you have poor radio link. You see, if your radio link quality is very good, then, well, look at the left bottom figure. Assume that this is what you are sending. You have some constellation diagram that's showing the possible locations, and this is what you are transmitting. If your radio link quality is very good, like the SNR is 100 dB, at the reception, the same constellation positions will be maintained. The angles or the amplitudes are always, they take on, in every symbol transfer, they take on the same positions. Or if you have different multipath components, you can get signal, but when you recover, your recovery is never confused. You have the same locations. So it's all good. You can have even more crowded constellation diagram. But you see, if your SNR gets, the radio link quality gets degraded, like SNR 25 dB, then you are getting different, because you get different components via multipath, and you get actually different locations. So there are some overlappings, and it is not a clear position then. If now left bottom is in a 10 dB only, even lower radio link. So it is more confusing. It's in a 3 dB. It's so confusing. So what may happen? The location, when you get it, receive a symbol, it may come with a position which is closer to a different position. Like, say, this guy should be located here when you receive. But at the receiving end, if it is shifted little bit, then the receiver will make a decision, and it may still assume that, well, it is pretty close to this particular position, so it will detect it as this one. But if it moves further, then it may come even closer to another location, and then can be misdetection. It can be detected as something located here. So you get then a different bit combinations then, because every particular constellation position corresponds to a particular combination of the bits. So when you're confused, if it is deviated too much and it is closer to another one, you are considering it to be a different position. You will have some bits in reception. Some of the received bits will be in error. Okay, not all. It's a combination that with the other combination, some bits may have still. It could be from 0, 1, 0, 0. It may be from say 1, 0, 1, 0. Then some zeros are correct still. Okay, but so all bits are not changed. So some bits will be in error. Now, if you have a very crowded constellation, when you increase the number of bits in a symbol, like you see, you have 16 different positions, whereas here you had only 4, or here you had only 8. So as you put the number of bits in a symbol, you have more positions, so it is more crowded, and it is more likely to have some misdetection. So if you have a pair radio link, you can have a crowded constellation diagram. You can put more bits in error, more bits per symbol. That will be more efficient. Your data rate will be higher. But if your radio link goes poorer, you should reduce the number of bits in the symbol. This is what we are trying to highlight in this presentation of the I mean, here we are actually trying to explain how you make some adjustments depending on the radio link quality. So adapt to the radio link quality can keep changing, and you need to adapt. Like the number of bits in the well, this is called modulation level. So in this case, your modulation level is 8. Okay, the modulation level here is like 16, or say 4 bits in number of bits. You have 4 bits, you have 3 bits. So the modulation level, higher modulation level means you put more bits, but that can be justified only when you have better radio link. So depending on the radio link quality, you should adjust the modulation level or the number of bits in a particular symbol. It's a quick calculation. You can, okay, the baud rate is given, so you calculate the bit rate. Okay, so then just see how many bits you have in a symbol. When you say 1664 QAM, means that you have quadrature amplitude modulation varying phase and amplitude, and you have 64 combinations. So how many bits are there per symbol for 64 QAM? May I ask you? You make sure you're not sleeping. How many bits do you have in a symbol when you have 64 QAM?
Sir, 6.
6, right? Okay. Now, handling packet errors. We know that the bits will be transmitted in the form of packets.
So, like,
Yeah.
I have a question, sir.
Yeah, sorry.
I have a
Any question? Yeah. Yeah.
question, sir.
Mm-hmm. Yes, please go ahead with your
So,
question.
like, is this connected to quantization?
Congestion? No.
Quantization.
Quantization? Yeah, it is. But quantization is an early step from when you convert them into bits. Analog form of signal is their information signal. You convert them into bits. So you first quantize in the amplitude, quantize the amplitude level, and then for different quanta or different segments, you assign particular bit combination. Okay, so that's a step you had before. I think you went through pulse amplitude modulation in pulse code modulation, PM, PCM. So then you had this quantization. Okay. So we're discussing what happens next when you transfer it. Okay, but you need some estimations of what is going on. There can be some bits in error, and it will be always the case if you have some wireless link. Okay, most of the time you have some bits in error. But how many of the bits are in error? So you need some estimation. Accordingly, you need to take measure. So it's called bit error ratio or bit error rate, BR in short. So the number of bits in error are ratioed by the total number of bits. Okay, or you can express it in percentage. In LAR or PLR, it's like how many packets or data blocks you are, okay, there can be some, you may call it blocks or frames instead of packets sometimes at the lower levels of OSI model. So how many of them, when you count in number of these blocks or packets or frames, whatever, when you count them, these packets you need to drop because they have errors. We cannot accept the packets. So and some packets may be good. So in terms of packets, when you calculate the ratio, it's called BLAR, block error rate, or PLR sometimes. Now, how to work with these errors? First of all, you can just check whether or not a particular packet come with some errors. So this is called error checking method, error detection method, or error checking. So two popular methods I discussed already: CRC, cyclic redundancy check, and checksum. The CRC is used in Ethernet, checksum is used in TCP, and you can check just whether or not there are some errors. That's it. But you cannot correct those errors. These methods don't allow any correction. But there are some more advanced techniques. These are called forward error correction. So in the these are coding. In short, it is called coding or line coding, which can some complex calculation to first detect which bits are in error and also correct. You may be surprised how I can correct. Okay, I'll give you a very simplistic example of the coding technique just to make you feel comfortable that yes, it is possible. So it is called forward error correction because one way you're sending from the transmitter to the receiver, you don't need any feedback from there. Just it tries to correct whatever bits have been in error on the way. So this is called forward error correction scheme, or FEC, or error correction code, ECC. So, but if you, but with all these schemes, you may still have the packets in error. It's not acceptable. You try to correct whatever bits are in error in a packet, but you cannot successfully correct all of them. So in that case, you need to retransmit the packet. This is what we have already covered in TCP. Then you need some feedback from the receiver. So these two methods, FEC and retransmission of the erroneous packets, they both together try to correct the information, or try to ensure correct delivery of the information. So example of the codes used for FEC. There are many different codes. You don't need to remember all of them, but please memorize the last three. They're very important currently. Conventional code, these are all, recently developed codes. Conventional code was used in 3G very popularly, and turbo codes in 4G, but turbo codes is more complex, or the competition load is very high. So sometimes a combination of convolutional and turbo codes are used. It is called CTC, convolutional turbo code. Okay, convolutional turbo code, or CTC. So sometimes CTC is used in mobile communication. And recently, 5G guys have selected LDPC. It's not, the spec does not prohibit the use of turbo codes, but LDPC can also be used, and LDPC is getting more popular. For some recent versions of LDPC has been very popular. WiMAX was using LDPC anyway. So a quick example to make you feel comfortable. Say, instead of sending just zeros and ones, if you send 3 bits, you want to express only 0 or 1. But, well, am I audible clearly? Is it clear? Do you hear me well?
Yes, sir.
Okay. I just wanted to make sure today's discussion is very important. So you wanna just transfer 0 and 1, but instead of a single bit, if you send 3 bits, and the first 4 combinations represent 0, and with 3 you have 8 combinations. So the last 8 combinations represent 1. Now some bits can be flipped on the way. So instead of when you're sending 001, well, okay, so maybe we take the first combinations. Instead of sending when you're sending 000 to express, you should send that. But on the way, one of the bits has been flipped. So from the transmitting end, it should always be 000 to express 0, and it should be all ones to express 1. But on the way, some bits can be flipped. So if it becomes 001 because of poor radio link, you still at the receiving end can poll the bits and see you have 2 zeros and 1 1. So it should be 0. It can decide. So similarly for 111, one bit can be flipped, but it can direct correctly. So this is like this is the simplest code. Okay. But the reality is the use of very complex codes, which comes with also significant computational load, even with the high with the advanced electronics today. Okay, but you understand that this will also not ensure always correct delivery. If 2 bits on the way are flipped, then there will be misdirection anyway. So you just increase the likelihood of correct reception. And if you had, say, 5 bits instead of, if you had the luxury to send 5 bits instead of 1, then you would have even better likelihood for correct reception, right? Out of 5 bits, 2 bits could be flipped, but you still can poll and get the right thing. But it comes with the cost that you need to send more bits than what the information contains. So the overall data gets lower. The overall data will be 1 if you do this coding method, right? Because for every information bit, you have to send 3 bits, but your data link has certain capacity. So that will be, you reach that capacity with just 1/3 information data rate. So how many, if I just take this particular example, say whether you send 3 bits or 5 bits or say 7 bits. Well, if your radio link quality is very good, is excellent, you don't need to use multiple bits. You just send directly 0 and 1. There shouldn't be any error on the way. But if the radio link quality gets poorer, you may send 3 bits. If it gets further worse, 5 bits, further worse, 7 bits. So then you can have better delivery, better correction. The radio link is getting worse, so you cannot send correctly. So this way you may be able to do, but the data will get lower. So a similar concept now we are getting, just like the modulation level. Depending on the radio link quality, you need to adjust the number of bits here compared to the actual bits, actual information bits. So this ratio is called code rate. Just number. So here you have 3 bits to transfer 1 information bit. So the code rate is 1/3, 1/3. So this is code rate. Code rate, number of actual information bits compared to number of bits in the packet. So if you lower the code rate, the reliability is better, but the larger the packet size or the so depending on the radio link quality, you need to adjust both modulation level and the code rate. So for any coding scheme, it comes with different code rate options. You can adjust the code rate, whether it's turbo core or LTPC, whatever. You can operate it with different code rate, and that code rate is adapted based on the radio link. Well, a term we didn't explain, error vector magnitude. This was like, say, in the modulation, in the constellation diagram, you could have a shift. I mean, you have a dislocation from the right location. It is shifted by the, if you draw, say, if it is supposed to be here, but the dot arrives here. When you receive at the receiver, you arrive it at the wrong location. So if you draw a vector between the correct location and the actual location, it is called error vector, because that represents how much error you have after reception. And if you take only its magnitude, then it is called error vector magnitude. So if you have poorer radio link, your EVM or error vector magnitude will be higher. So then you should have a lower modulation rate. So these two things, modulation and code rates, are adapted together. It's called modulation encoding scheme, MCS. Now let's assume that a user has moved closer to the base station. He was at a far distance, but he now moves. So as he moves, his radio link gets better. So it is then higher CINR. Why? Because the carrier power from the base station will be higher, and also the interference will be lower because he's not further away from other co-channels. So the error vector magnitude will then be lower. Okay, then you should have higher modulation scheme, higher modulation level, and higher code rate. That will increase the number of bits transferred, right? So, for example, it might have been 16 QAM before, then you jump to 64 QAM. So instead of 4 bits, you put 6 bits in a symbol. So the data will be a lot higher. So you can enjoy that. Now it is all right because too many bits will not be in error. And the code rate you increase from 1/3 to half. Okay? So the modulation coding scheme is adjusted. So then you get higher bit rate or higher spectral efficiency. But it is the other way around. If you go, okay, so now it says that if your adjustment is not correct, what happens? A user has moved further away, so lower CANR, error vector has improved, it is higher. But you have a wrong adjustment. What do? You increase the modulation and coding scheme. Both modulation code rate and modulation levels are increased. What will happen? Hey, someone has his microphone unmuted. So what will happen then? There will be too many bits error. Okay, right? Too many bits will be error. So too many packets will be in error. So you need more packets to be retransmitted. And as you keep retransmitting so many packets, the overall data rate will then be lower. So although, hey, someone is enjoying cricket, and please keep even if you do that during the class, well, I did allow it in the beginning of the course, so I cannot forbid now. You can enjoy cricket, but mute your microphone at least. Well, so what will happen then? See, there will be too much packet retransmissions. So although you are putting more bits, okay, the data rate will not be able to improve. In a symbol, you have more bits, your code rate is higher, but you're sending too many bits, you're pushing them, but you also have to retransmit many of the packets. So you cannot just keep sending the packets. Much of the time you spend retransmitting. So the overall data rate, instead of improving, will degrade. So you get spectral. So probably you now understand that you should always adapt. The MCS should neither be higher nor lower than its current appropriate level. So you need to monitor the radio link quality, and accordingly you should adjust, right? So there are different MCS levels defined. Like in the number of definitions, number of MCS levels are improving. So you can better tune to the, I think I can, okay. You see, in the case of GSM or GPRS, there was GMSK, I mean a single modulation level. It is some type of FSK. GMSK is a type of FSK, variant of FSK. But there was 4 different code rates, but a single modulation level. In the case of age, there are 4 code rates with GMSK and another modulation level, 8 PSK, which puts in GMSK you have just single bit in the symbol. In 8 PSK, you have 3 bits in a symbol. So there are 5 code rates under 8 PSK and 4 code rates with GMSK. So 2 modulation levels, but in total 9 different levels. 5 code rate levels with 1 modulation and 4 with other. So in total, so this is called MCS levels. In total, 9 MCS levels. Okay, MTS uses QPSK and supported, but I mean HSPA handles things more like what we wanna discuss. Okay. So here in HSDPA, it was 8 QPSK system com HA before, but later actually they increased the number of possible levels. HSP plus 464 QAM. Okay, so hold it for HSDPA, GPS can 16 QAM, HSDPA only BPSK, but HSPA plus supports 64 QAM in downlink and 16 QAM in uplink. LT supports QPSK 16 QAM and 64, 3 different modulation levels, and both in downlink and uplink. In release 12, 256 QAM was also supported, but for downlink only. In release 14, 256 QAM was also supported in uplink. And from release 15 onwards, which is actually 5G, 2024 QAM is supported. So LTE supports up to 256, and 5G supports up to 2024 QAM. 2024 QAM means you have 10 bits in a signal. The number of modulation MCS levels you have for GPS, as I said, only 4. For age, you have 9 MCS levels, 4 under GMSK, 5 under 8 PSK. For HSDPA, there are 16 MCS levels with 2 different modulation options. So a number of code rates. With LTE or 5G, sorry, I'll add 5G here. I'll correct this slide. With LTE and 5G, it is always 27 MCS levels. Okay, the number of possible modulation schemes can be 3, 4, or 5, up to 64 QAM, up to 256 QAM, or up to 1024 QAM. But the total number of MCS levels is always 20 in both downlink and uplink. Anyway, with higher number of MCS levels, you can better tune to the current radio link. The radio link quality will keep varying. So if you have too many levels, then you can.
Excuse me, sir.
Yes. Yes, please.
Sir, the Isha prayer configuration is at 7:30. So could you take the attendance right now?
Well, even the attendance would take a while. How about we take a break and then come back?
But sir, after Isha prayer, we're gonna have to take dinner, so it's gonna take like 40 minutes at least.
Oh, sorry. We should have started earlier. It could have
Yes,
been
sir.
6 instead of
Sorry.
6:30. Right? So suggest me what we can do. I would also feel better
Sir,
if
you can
I
take
could
that.
join. Okay, what
Sir,
about
So
we
maybe
can hold the
take
class for
the
15
attendance
minutes.
right now,
okay the
and
attendance?
then
We have only 4 minutes
those
left.
of us who have to attend the prayer, we can
Well,
go
I
to
mean,
the prayer, and the rest of us can do the
when
class.
when you remind it, it's only 5 minutes. I mean, it's only 4 minutes from now, the prayer. Well, what if we, I mean, for now we keep everybody present, but you allow me another half an hour or say 40-minute slot tomorrow. I just need time to finish so much stuff still left. So if you allow me some another time, I mean today, late tonight, or tomorrow, or whenever, if you can give me enough time slots, it's all right for me. Then we can wrap up right now. Then we can
Sir,
also
I
attend
think,
the prayer on time.
sir, am I audible, sir?
Yes, you are. Yes, you are. Please go ahead. You're audible. Hey.
Sir, can we give like 1 hour 30-minute slots for the next two classes if possible? So these 30 minutes will be covered, or rather for 15 minutes.
Okay. Okay.
In one of the class, we'll give you 1 hour and 30 minutes slot so that
Okay.
these 15 minutes are covered.
Okay. Not 15 minutes. Oh, yeah, around 15 minutes. Okay. Okay. That sounds better. So we're stopping right now. Later, you manage time anyhow. Thank you. Thank you for joining today.
Thank you. Thanks.
Assalamualaikum.